Hello, welcome to Lesson 7.4 on geometric sequences and series. Geometric sequences and series are fairly straightforward. Before we get into describing them, I'll just give you an example of one, and I'm sure you'll kind of pick up pretty immediately on what they are. So here is a series of numbers that we would call a geometric sequence. 2, 4, 8, 16, 32, 64. Okay, that would be an example of a geometric sequence. Geometric sequences are just sequences of numbers, a list of numbers, which are a series of multiplication steps over and over. Basically, a different way of thinking of it would be if you generated an exponential function, so like 2 to the x, 3 to the x, 4 to the x, something like that, and you looked at the table of data and you just went down the values in the table, that would be a geometric series. If we want to look at the definition from the book, a sequence is a set of numbers in a particular order or pattern. Each number in a sequence is called a term. The first term of a sequence is denoted A1, the second term is A2, so it's just kind of our notation here, and so on. A finite sequence contains a limited number of terms, while an infinite sequence continues without ends. A sequence can be defined as a function. Today's goals with these things are to generate some geometric sequences and to find sums of geometric sequences. There's a variety of vocabulary to understand, like sequence, term of a sequence, finite sequence, infinite sequence, geometric sequence, common ratio, explicit formula, recursive formula, geometric means, series, geometric series, and sigma notation. We'll get to these throughout the lesson, and we'll define them as we get to them. Okay, so key concept here. A sequence is a function in which the domain consists of natural numbers and the range consists of real numbers. Okay, so when we say the domain consists of natural numbers, we're saying that we're not doing, when we have 2 to the x and you look at that graph, that is a continuous function. So you can look at 2 to the first power, to the second power, to the third power, but you could also look at 2 to the 1.5 power, to the 1.4, to the 1.444. You can look at all these decimals in between, right? It's a continuous function. In a sequence, we are not talking about continuous functions. We're saying that the domain would just be like x is 1, 2, 3, 4, 5. It would be a discrete function that on a graph would look like a series of points unconnected to each other. So our domain here, 1, 2, 3, ... up to n, up to whatever the final term is going to be. And then we just we denote those terms using this notation A1, A2, A3. So this would mean the third term in the sequence. This would mean some nth term down the line. In a geometric sequence, each term is determined by multiplying a non-zero constant by the previous term. Okay, so it doesn't need to be 2, 4, 8, 16. You don't need to be multiplying by 2. You could be multiplying by 2.1 or 2.2. The constant that you are multiplying by each time does not need to be an integer. And the value that we use to multiply is called our common ratio. So if, for example, we were going to do like 3.3 to the x, then 3.3 would be our common ratio. The nth term, a to the an of a geometric sequence, in which the first term is a1, and the common ratio is r, is given by the formula an equals a1 r to the n minus 1, where n is any natural number. So if you look at this, what we're saying is that you're taking your first term in a sequence, we're taking our starting position. So let's say that we're going to do a sequence of numbers. Let's do doubling, but let's not start it at 2. Let's start it at, let's start at 5. Okay, so a1, my first term, could be 5. If I'm doubling, my common ratio would be 2, so r would be 2. And then this is saying that some number in the sequence is going to be the first number times the common ratio raised to the power of n minus 1. So if we wanted the third number in the sequence, for example, if we were going to start at 5 and we were going to double and we want the third number, well, we go 5, 10, 20, right? So the third term, A3, should equal the first term, 5 times the ratio 2 to the 3 minus 1 power. Okay, and let me write out a little table. That'll kind of make more sense of this. So if we are doing 5, 10, 20, 40, if we are doubling each time, that means that if we want to get to this is going to be my first term, my second term, my third term, my fourth term. If I want to get to this fourth term, if I want to make it out to here, the amount of times I need to double 3 times, right? I need to take 3 steps down this list to get to that fourth number. So that's where this n minus 1 comes from. If n is 4, if we're looking for the fourth number, if we're trying to figure out what that fourth position is, then we don't want to take 4 steps to get there. We want to take 3 steps to get there. So that's where the n minus 1. So 4 minus 1 would be 3, which means that if we have an exponent of 3, we're going to be doing this repeated multiplication 3 times. So whatever the number is that we're multiplying by, in this case 2, right? We're doubling each time. We're going to do that 3 times to get to our fourth position. Okay, so that's where this general formula is coming from. An explicit formula, like the one above, allows you to find any term an of a sequence by using a formula written in terms of n. A recursive formula allows you to find the nth term of a sequence by performing operations to one or more of the preceding terms. The recursive formula for the geometric sequence is a little different. It's written as an equals r times a to the n minus 1, where a n minus 1 is the term in the sequence before the nth term. Okay, so what are they saying here? They're saying that, for example, once again, if we want to find, let's just use the same example, if we want to find the fourth term, if we want to find a sub 4, then that's going to equal 2, our constant that we're going by. So we're going to double a to the n minus 1. So if n is 4 right now, if we're looking for the fourth term, then this one represents the third term, right? N minus 1 would be 4 minus 1. So we're saying the fourth term is the third term times our constant, right? Or the fifth term is the fourth term times the constant. Every term in the sequence is just the previous term times the constant. And in this case, in our example, our constant's 2. So if we wanted the 100th term, a sub 100, sorry, then we're going to take the 99th term. We're going to take 100 minus 1. We're going to take the 99th term, and we're going to double it. So it's just 2 different ways to express it. This way is simply expressing that each term is the previous one times some constant. And this expression kind of bundles all that information together and says that any term is the first term times some constant exponentiated a certain number of steps. Okay, so we're either just, this one is really just talking about taking one step, right? This is talking about the difference between some term and the term before it. This is talking about the difference between some term and the first term. Those are the 2 different ways to think about this. So the explicit formula compares the first term to any term in the sequence, and the recursive formula compares any term to the one directly before it. They both have their own kind of convenient use cases.